Hello and welcome. You are looking at symmetry. Now, unlike my transformation slides, I will not be jumping into the next slide defining the words pre-image, image, and isometry, because those slides are focused a little bit more on those transformations. If you want to know what those terms mean, I would advise that you watch the beginning of any of my videos on translations, reflections, rotations, or dilations. But I will be using the terms. You might be able to connect them even if you don't know them. But as I move on, I'm going straight into symmetry. Symmetry occurs when you have isometric figures on opposite sides of a dividing line or about a fixed point. So one or the other will occur, and it's either going to be called line symmetry or rotational symmetry. Line symmetry occurs if a pre-image is reflected over a line and its isometry is a reflection of the pre-image. So I'll give you some examples as we do that right here, and then I'll talk about rotational symmetry afterward. So in this example here, we have some figures. All of these have symmetry somewhere, line symmetry somewhere. And what I'm going to do is seek them out. Basically, if you think of these like the opposite of when we transform something and then we create the image as a result, and the line of symmetry was already drawn for us, and we now have something symmetrical. Now we have something where we have to find out where we draw the line to make it symmetrical, such as we would have a pre-image flipping over this thing to make the image. So for instance, this square here, if you think about what it means to have line symmetry, I'm going to draw one right now. It's basically, if I draw a line right down the middle of this, what you're given on opposite sides of this square, let's say this was a point called A, I could essentially call this point A prime. This is about the same thing as reflecting this point over this line here to get that one right there. And maybe the square is called ABCD, in which case you have to know that A maps onto B after it's reflected. Same with if you called this C. This could be called C prime in the sense that it's reflected over, and that could be the image of that point. But if this is square, well, I guess it's square ABDC. If it's square ABDC, C maps onto D. And all these other points map onto other points, not just the vertices. Maybe there's a point right here, E, and then there's a corresponding point here, F. Maybe there's a point that's not even on the square. Maybe it's right there, G, and there's a corresponding point that's H. No matter the case, this line here ends up creating symmetry on both sides based on the square itself. So that's one line of symmetry that this square has to offer. There's another one that's the same thing going through a different set of sides right here, where the same thing, if I reflect this point, it goes over there, etc. Now these aren't the only two lines of symmetry. There's also another one if I go diagonally, literally through the diagonal right there. If I look at this one right here, you'll see points corresponding here and here. I won't write all the letters, but those two, if it flips over that line there, right here, if I go perpendicularly to it, over here on the other side is a corresponding point, and that exists in a square, and if you can imagine that one has it right there, then so does this diagonal right here. So all four of those diagonals, they do go through kind of that center point as well, and they are all lines of symmetry. Just one at a time though, but you can draw all of them. Now here's a right triangle, and it's an isosceles. Assume this is an isosceles right triangle, meaning these two sides are congruent, these two angles are congruent, this angle's right. Now, as we have this isosceles right triangle, notice that drawing something straight up and down, just because you're dividing it in half, if you want to call it that, doesn't mean that it's symmetrical on both sides, so that makes no sense. Same with this. It makes no sense to draw something there and just say, well, it's symmetrical. The only one that seems to work here is if I draw a diagonal through here, because what you start to see, once again, are corresponding points. This point and this point, when reflected across the line, correspond, and as we get closer, over here, once again, these points even correspond as well. This one only has one line of symmetry, this right triangle. I couldn't make another one. I couldn't draw it across here and say that a point here corresponds with this point right there. It doesn't. Let me make sure that makes sense. When this line reflects, and this point reflects over the line, there should be another point right here on the triangle that would match, and it does not correspond with it. So there's only one line of symmetry for that. The rectangle, much like the square, does have lines of symmetry going left and right and up and down through it, but the diagonals don't work anymore, and this is one that people confuse for thinking there's symmetry. So I'm going to erase the two that I already gave you before right there. Let me take those out for a moment. Let's take a look at this one. Much like that right triangle, if this was truly symmetrical on both sides, right here and right here I have corresponding points, sure, as they reflect across there, but as I go closer to the corner, if I drew a perpendicular line through that, then on the other side you would probably also see something there. But it doesn't really look like that's the case. As you can see, these angles aren't even congruent, much the same as this ain't looking like the kite that I wish it was. So that's not exactly how this thing works. The only two ones that truly exist, if I keep pressing my own undo button, are these two right here. This arrow, line of symmetry, the only one that shall exist is the one that's going straight up and down through it. So as you see these a little bit more, you start to understand why some things don't have symmetry. You have to think about what a mirror image is. Now a regular hexagon goes up and down, even left and right through there, all the vertices and all these other sides it should go through. I'm just going to give you something that you might have been able to conjecture after looking at a square and this as well. The number of sides of a regular polygon also determines the number of lines of symmetry there are. Now I did say a regular polygon. So for a right isosceles triangle there was only one, but for an equilateral triangle there would have been three. For a regular hexagon there are 6, and you can imagine for a regular pentagon there will be 5. 1, 2. These won't be perfect, I apologize. 3, 4, and 5. And they all kind of exit the same way. When we deal with rotational symmetry, you'll understand why this is the case. Now a circle, as you can see, all these have been going kind of through the center for regular polygons. Circle would also go through the center of. Difference here is, as I start to draw a line of symmetry down through it, you're like, yeah, sure, there's one. How about this one? Oh, of course, yeah, how about diagonals? Is there a limit to how many I can make? As long as there's a diameter going through it, it doesn't seem like there's a limit. A circle has an infinite number of lines of symmetry as long as it goes through the diameter, or as long as it's drawn as a diameter, then it is a line of symmetry. So as long as that makes sense, I think you'll be good to go. So that's what lines of symmetry are in comic geometric shapes. I don't know if an arrow is really all that common. Okay, your next example here is with rotational symmetry. So let's look at that. Rotational symmetry occurs if a pre-image is rotated about a fixed point and its isometry is the same figure. So we're going to rotate these objects a certain number of degrees to see if we can come back to how the object appears. Now thankfully, because of my tool here, when I click on this, it already highlights and it treats the center point of this shape as exactly that. So that means when I rotate this, it'll rotate about the center, which is perfect. What I'm going to do with this square to start with is say, as I start rotating this, how many degrees does it take before I'm looking at a square again of the same orientation? As you can see, I rotated it 90 degrees, and it doesn't matter which direction, by the way. I could have done it clockwise, I could have done it counterclockwise, but I'm still getting 90 degrees rotation before I end up with a square of the exact same mapping, right? It's an isometry. Now, as I rotate it again, you can see another 90 degrees to 180, I get that. And like I said, as we went back here, 90 degrees clockwise is the same as 270 counterclockwise. So a square is said to have not only rotational symmetry, but its rotational symmetry is at 90 degrees. So it has 90 degree, I'll just put RS, 90 degree rotational symmetry. Now another way to figure that out, because you obviously don't have a super fine fancy computer tool here, is let's say you kind of draw a center, at least for this regular polygon, and you'll see they don't have to be regular, but you will see some certain things that they will have to have. If you've practiced rotations before of figures, then I think that you understand how it is they look after pre-image and image are rotated and what it means to have rotational symmetry. What I did was I drew a center and I drew radii, yes, these are called radii, from the center to the vertices of this regular polygon. And as I do this rotation one more time, do it again, I want you to take a look at how this thing ends up looking after you rotate it. Well, it ends up looking just as it did, and it should. So the question is, there are central angles around here, and what I want to do is determine what the degree of each central rectangle is. So as I rotate here, how much did it rotate? We said 90 degrees. So the central angle there, that much that it's rotating is 90 degrees. So each of these are 90. Now what's another mathematical way to figure that out? Well, at least in a regular polygon here, all of these central angles are congruent, and there are 4 of them. Central angles, as you can see, kind of builds up a circle. It adds up to 360. So 360 divided by 4 equals 90. That's where I'm getting that central angle from. Okay, triangles are going to be the same way. Now, I'm not going to spend time doing this for every single one. I want you to take recognition of what's happening, and you have to think about what it is that will get you there. Now, I'm not going to do central angles every time. That's best to be done for regular polygons. What you really should do is just say, how long does it take me to rotate? That's what? Not all the way there, but how long does it take for me to rotate before I land on a shape of the same, thing? Now, this isn't rotating about the triangle's perfect center here, but as you can see, it took this amount, about a third of a full circle, 1/3, 360 divided by 3. It took 120 degrees rotation for this to actually take place. And if you want to take a look at that, think of the central angles that are being drawn. These 3 right here. There are 3 central angles, all congruent, so that gives you 120 per. So triangles, equilateral, an equilateral triangle has rotational symmetry at 120 degrees. As you can see, as I keep rotating, it's kind of an off rotation, but as I rotate there, that's 120, 120, etc. Okay, a parallelogram, how long will it take me to rotate this one? So you just have to think, when I rotate it here, that is not symmetrical with what this was here. So 90 is not going to fit the bill, neither will 120. It takes a full 180 degrees before I get back to where I started there. So what's going to happen here, watch this, I'm going to keep this here. As I press the undo button, it essentially brings me back redo, undo, redo, undo. That has rotational symmetry at 180 degrees. Okay, so let's go ahead and write that. This is 120 degrees, this is 180 degrees. Not so much referencing the central angles and whatnot, but just showing when you rotate that, that's what happens. A pentagon, if you think about, once again, how many rotations does it take? Well, okay, how many of these? So here's one rotation to get rotational symmetry there. The question is, how many degrees is that? 2, 3, 4. We've completed our cycle at 5. It took 5 full angles of rotation, of rotational symmetry, to get back to where we started. So what's the angle of rotation? 360 divided by 5, that's 72 degrees. So as you can see, this kind of does as it does. I'm going to start speeding this up a little bit here. The star, again, 1, 2, 3, 4, 5. That's also 72 degrees rotational symmetry. So it's not always about a center. Central angles are helpful, but that's also helping describe what it is that you're actually doing. Now here's a trapezoid, and trapezoid may have had line symmetry if I went right down the middle, but as I rotate this, you'll recognize here, even if I go all the way to 180, well, this is not the same thing. If I go all the way to 180, not the same thing. Now, if it takes you going past 180 to find rotational symmetry, hint, you won't find it. This one has no rotational symmetry. The fact that it took me a full turn to get all the way back to 360 is the only way that made that possible. No rotational symmetry. And the regular hexagon, 1, 2, 3, 4, 5, 6. It has rotational symmetry at 360 divided by 6, which is 60 degrees. Rotational symmetry of 60 degrees. Now, state if any have point symmetry. Now, point symmetry is present when a figure has rotational symmetry at 180 degrees. Now, you might say, oh, okay, well, this one has point symmetry, and you'd be right, this does have point symmetry. But just because the rotational symmetry of the object, the smallest amount of angle of rotation, is 180 degrees, doesn't mean those are the only ones with point symmetry. Take a look at the square, for example. I can rotate at 180 degrees and still have symmetry. Oh, that was kind of cool. I can rotate at 180 degrees and still have symmetry. Therefore, a square has point symmetry. Here's another way of thinking about it. If your angle of rotation is a factor of 180, if it takes so many multiples to get to 180, then you have rotational symmetry, or sorry, point symmetry. But take a look at this triangle, for instance. When I rotate this guy around 180 degrees, not the same thing. And that makes sense because 120 is not a factor of 180. The next multiple of 120 is 240. So let me start checking off which ones have it. Square, rotational symmetry, parallelogram does. Pentagon, multiples of 72 are 72, 144, 216, up, surpasses 180. And that also makes sense. If I flip this around, this would be an upside down pentagon. So also not point symmetry. Star would be the same, no point symmetry. Trapezoid had no rotational symmetry whatsoever. And the hexagon, 60, 120, 180. You bet this will have point symmetry. 60, 120, 180. So this also, too, has point symmetry. And that's what it means. So let's check that one off as well. These three do. I'll underline that to say check. Take a look at the blue check marks. Okay, and last but not least, a lot of brand logos also have line symmetry as what rotational or point symmetry. Name the types these ones have. So I'll just go ahead and just give labels R or L or P or whatever else. I'll give which ones they have. Now, Xbox symbol right here, you'd think it might have rotational symmetry. The problem is this X doesn't quite look the same when you turn it around or even this way or whatever else. So not quite rotational symmetry, and that's probably what you'll see about with a lot of these brand logos. Not fully what you want. Some of these will only have line symmetry, and when they do, it might just be down the middle in one case. Now, what I mentioned before was something regarding how line symmetry can be used with rotational symmetry. Is there line symmetry going across this way? The answer is no. Because what you could do, theoretically, is you could rotate this to the extent that once this left and right one is faced up and down, take a look at it up and down. It's probably easier to see reflection. Is this reflected the same way? The answer is no. Even if this had 90-degree rotation, if this had 90-degree rotational symmetry, then this would also be symmetrical this way. Now it doesn't have 90-degree rotational symmetry, so that doesn't work. So it has line symmetry, and the only one that I drew was right there, and that's all that it has. So I'll say line. This one right here, if I go down the middle, looks like we're good there for line symmetry that way. So taking a look at that example that I talked about, if this has rotational symmetry, I shouldn't have said at 90 degrees, but if this has rotational symmetry here, I'm sorry, I said at 90 degrees here for the Xbox thing. I meant at 180 degrees. If this has rotational symmetry at 180 degrees, then this would have had line symmetry here, which it does not. So let me flip this one around and see if it still works to have that one there. If I rotate this, I guess that works. But if you rotate this here, does it still have that? Yeah, it does. I guess you could argue that the lighting on this thing, you see that ball, that it's a little lighter on top than on bottom. I'm not going to get that antsy about it. Now, what about the diagonal lines? If I go diagonal, is this symmetry? You have to think about the fact that this white here, okay, it should be going up this way if it had line symmetry here. So it does not diagonally. So this has line symmetry, as you saw. It has rotational symmetry at 180. Therefore, it also has point symmetry. Starbucks. Line symmetry down there. That's it. Not going to spend too much time on a lot of these. Line symmetry down there. That's it. I don't know what that is. I think it's a shoe company. Pepsi. This one's interesting. Not quite line symmetry this time, because you can see this point should have a point mapping over here. It does not on the white. So not there, and also not here either. This almost could or would have rotational symmetry. You argue, if you're not looking at color, that it would have rotational symmetry at 180 degrees. So take a look at that. So I might mention that it does, because I'm not really referring to color. I'm talking about the design of it. So let's say it does have rotational symmetry at 180. Therefore, it also has point symmetry. The Audi symbol, again, the chain link stuff, you could say, okay, this doesn't have line symmetry because of the whole chain link thing. Well, let's not get that particular right now. Let's say it's got that kind of line symmetry there and there. That's only nice to say. But how about rotational symmetry? 90 degrees, no. 180 degrees, yeah, let's say it does. And if it does, then it has point symmetry. Again, the lighting. I don't want to get too particular, otherwise almost none of these would have what it is that we want. Volkswagen, line symmetry, nothing else. If you're taking a look at that W, that would change the effect. I don't know what this is. Coach purse, something like that. Line symmetry, that way. Rotational symmetry of 180 degrees. As you can see, I'm speeding up. I'm almost done with this whole thing. Rotational symmetry at 180, we're good to go there. Looks like we're not getting 90-degree rotational symmetry ever. Honda, the H is taller in one sense, so only line symmetry this way. It would not have been this way. No rotational symmetry for the same reason. It doesn't go that way because if I turn it 180 degrees, you can see it looks different. It clearly looks different as opposed to the Pepsi thing, just different colors. And Toyota, also line symmetry. So So it looks like these aren't the best examples, but they do have it here and there from time to time. A lot of them have line symmetry going down the middle, which is true about a lot of logos, at least brand logos with an emblem that you're looking for. Okay, that's it. Fin.